So this is the second part of this is the second segment. So the previous speakers talked about the use cases. So we are going to focus mostly on the implementation side. We are not going to cover a whole lot on the pooling usage. We'll essentially focus on what's out there currently available, both from the silicon vendor, device vendor, as well as the operating system viewpoint. What is that is actually currently available for us to actually start working within the OCP sub-project umbrella. So we are calling this as a software-defined memory ecosystem readiness. So we have several vendors that are actually going to talk about, so there are two parts to this one. So the vendors are actually going to talk about how they are actually enabling and supporting the use cases to drive the TCO and data center memory footprint infrastructure reduction using CXL as one of the fundamental building blocks. And then we'll also cover the operating system viewpoint. So we are going to cover the Microsoft, we are going to cover the Linux, as well as the VMware. So you get the flavor of both the actual hardware availability as well as how hardware can be used within the context of operating system of your choice, be able to actually deliver a solution to meet the use cases that they talked about in the first section. With that, let me hand over the discussion to Rekha. Rekha is going to cover the Samsung, the portfolio, hardware portfolio. Rekha.
Thank you.
Maybe it is. I think that's yours.
Okay. So I'll cover the memory devices from Samsung. Right. So Reddy just presented about the different components that are going together. So Samsung being a memory vendor, I'll cover what we are doing in, from the memory devices perspective to enable the software-defined memory ecosystem and what are the ingredients that we are working on. So from the compute perspective, you have the cache, right? So now we are talking about lots and lots of memory. And when that gets huge, then you also need larger last level caches. So we are working on LLC DRAM products with high bandwidth and capacity. And the compute devices, the GPUs and even the CPUs going forward are going to have HBM. So we do HBM as well, and now we are also working on HBM PIM, which is processing in memory, right? So on the HBM itself. So we talked about the near memory, which you all know today, which is the DIMMs, and that we are having the DDR5 products, and you can actually check that out in the Samsung booth as well. And the main components that I'll be covering today will be the far memory and the pooled memory solutions that we are working on using CXL. That's going to enable this software-defined memory ecosystem. So the first one here is the CXL-based memory expander, which is basically DDR products, the DRAM product using the CXL channel. And I'll go more over it in the later slides. And we also have something called the Memory-Semantic SSD, which puts the NAND flash SSD in the CXL bus. So there's also one more aspect here from the whole memory ecosystem perspective. It's the processing near memory devices using CXL protocols. And this is something that we might be able to look at using this forum, the composable memory systems, or together with the computational storage and memory technology group. So I'll primarily cover the memory expander and the Memory-Semantic SSD here. So the first here, memory expander, this is also something that you could check out in the demo booth, the Samsung booth. And we had announced previously FPGA based version. Now what we have is ASIC based version, the CXL based memory module, E3.S form factor, and with CXL 2.0 specification, with DDR5, with viral data poisoning, RAS features, media scrubbing. And the second aspect that we have all been talking about is the pooled memory aspect. So what this enables the pooled memory is, if you really needed the memory that needs to go beyond your DIMM slots, what the traditional systems have to do is go beyond the server to the next CPU or to across the network switch to another server to access the DIMM that's attached to that CPU, right? So you have to add the compute along with the memory. But with CXL, what this enables is direct attached CXL memory expansion over the PCIe slot, right? And that is the medium memory, that's not the near memory. And from that, you can also go not just over the Ethernet, but also over the CXL switches, multi-level switches for pooled CXL memory expansion. So we are working with partners on switches and enabling these solutions with pooling across the nodes, across the server, and showing this in a demonstrating the use of this and the performance. The performance for both direct attached and for pooled memory accesses, if you are more interested in them, please go and talk to the Samsung booth, the people at Samsung booth. Right, there's also the memory tiering solutions that we talked about, and there's the software defined aspect, there's the application control, you have the OS level or application level solutions. So different solutions work for different needs. So we are working on both of it. This is SMDK, the Scalable Memory Development Kit, which is the application level, but we are also working in the kernel level memory tiering solutions as well to enable the different devices and the pooling and tiering solutions. So the next off is the Memory-Semantic SSD, right? So people talk about TCO and how do you enable the so much memory, the DRAM is not scaling as much as the requirements are, and how do you go beyond that? What today TCO conscious memory expansion is doing is expanding over NVMe SSD and paying a software overhead and an IO tax to go and access this more than required amount of memory using the block access instead of the smaller scale, smaller granularity 64-byte, 128-byte memory accesses that's typically required by this system, right? So you have to move data around and move data, do more data copies, which increases the cost and is making it harder to do expansion over NVMe, even though TCO perspective price point, that is what is making more sense to them. And that's why we have this CXL-based Memory-Semantic SSD concept. So what this provides is two options here, right? So the first one is the dual mode concept. What it does is exposes the entire NAND space as memory and also as storage. So as storage as a legacy NVMe SSD over .io protocol, and you can use your regular file system that you have typically used, no change there. And then the same file, once you actually memory map it, the same data is now exposed as memory as well over load store semantics over CXL.mem, right? So typically what you used to do with this memory map is behind the scenes you would do IO, but with what we have enabled here is behind the scenes, the actual data area is mapped through CXL protocol, so direct access from CPU caches through the CXL protocol to the memory. Right, so you don't need to copy anything into DRAM to access it. You can directly access it from the SSD. And there is also a DRAM cache internal to the SSD for that accesses. So the higher, hotter data are served from that for better latency. And the next option here is what about typical critical path workloads that write lots of small data and read and write and expecting very high performance and persistence like metadata, log writes, indexing, things like that. So, and people who have been used to obtain persistence memory, right? So, what we provide here is persistent memory mode, and what the media here is not opting, right? The media here is DRAM plus NAND. The DRAM space is now what is exposed as memory, and NAND behind the scenes is available only to provide the persistency. And there's an external power connector that can be attached to external power supply or battery connection to provide the persistency guarantees, right? So, what you need to consider here is the persistency needs are provided, but the performance and the cost trade-offs are different from what you are used to with Optane, right? So, this serves some of the needs of the data center workloads. So, for TCO conscious near, far and pulled memory options, so we are providing DRAM memory expanders, Memory-Semantic SSDs. So, over PCIe PCIe lanes, now you can expand memory, and you can also go beyond the node through switches to access the pooled data memory. And you don't have to do I/O swapping and data copies that you typically did before, and what you can now do is directly access the data in NAND without any copies required, and you can achieve larger memory widths at lower TCO. So, with that, I'll hand over to Mahesh.
Thanks, Rekha. Is this on? All right. Before I begin, just a shameless plug for SCM. I'm a relatively new member to the team. Alex Branover covers AMD, but they've really welcomed me into the team. So if anybody is here who's thinking about joining it, great bunch of people working on solving the problem. So again, please feel free to reach out and join the team. As I was thinking about the ecosystem readiness, my team at AMD works on enabling CXL. So we spend quite a significant amount of time working with our partners, our customers, on enabling CXL solutions. So we work very closely on the use cases. And what I was thinking about today, we live and breathe this thing, so I was thinking about we should really be talking about what is the ecosystem readiness, what are the things, and start to focus on what is out there that is laying the foundations of composable system memory. So that's the sort of topic I wanted to go with. So the first one was more about system flexibility. So this just starts with just thinking about what does CXL offer, right? I mean, one of the parts about CXL is you get the flexibility to determine whether you're going to put a PCIe card or a CXL card and then get the flexibility. So from a composable system perspective, it's already built. All of the solutions out there are giving you that flexibility. The next piece of it comes is, do I make a choice of by 16, by 8? What do I do, right? What do you pick? And at that point, you're looking at that flexibility to decide when I'm going at a lower data rate or lower number of lane count, I don't want to sacrifice the other lanes, right? So we need to think about that composability from that perspective, that you're providing the lane count, but you're not sacrificing your total available PCI Express lanes and bandwidths. So those solutions are available today. So as we're looking at the ecosystem that's building up, it's really important to think about what's available and think about what's the lane count you're going to pick as the foundation for a composable system. Now what comes along with that composability is also media type, right? So if you're thinking about DDR4 or DDR5, right? If it's a DDR5, you're looking at, okay, by 8 Gen 5 is going to give me one channel of DDR5 4800 bandwidth, right? But it gives you the choice to say, okay, how much capacity, what's the bandwidth do I need? Am I going to pick by 16 or by 8, right? So solutions are out there that provide that. There are controller vendors that are providing you a solution with by 16. There are others who are providing by 8. And finally, from a system flexibility perspective is the form factors. So we're seeing various different form factors that are getting deployed. Either they are custom form factors, in which case you're looking at DIMM reuse and DIMM replacements, in which case you're just plugging in DIMMs, right? So that's one use case. There are others that are chem form factors. And then you're looking into E3.S or E1.S sort of form factors that are drive modules. And as a CPU vendor, we have to think about providing support for all of those form factors as they are going in to come into the market. But what we're seeing is that all these form factors are what our customers are going to deploy. And that would be part of this composable memory system where you need to think about what are the form factors, how are we going to address it in a composable manner, in which case I need to understand what's out there and program. So we need to build that understanding through our solution space, and this work group can help address that, right? So that's one part of it. But it's all available, it's all coming to market, and within the next 6 months is what I'm thinking. The next one is really expansion, right? So this is where you think about, okay, now that we have a solution, what are the things that we need to focus on, right? A lot of it is either you're doing it for capacity or you're doing it for memory bandwidth. And the question, I've been saying this, that with CXL, the first thing that we have to go and prove is that CXL attached memory is functional and performant. So if you look into what has been done so far with all of the prototyping FPGAs that are out there, I think we've proven the functional part of it. That can a CXL attached memory work and function? Can it appear as a NUMA node? Can you launch workloads? All of that work is done. I think a significant focus that is out there in the ecosystem right now is it performant, and work on optimizing with the controller vendors to get that performance to what we've been calling remote socket latency and performance expectations, right? So I do believe that the solutions are out there and we will hit it with that, but this is a key piece because everything depends on this for CXL to make sure that the very first expansion solutions are there that are performant. Right. So, and a lot of focus, my team spends a lot of time working with the community in enabling that. Along with that, the other part is, and I think Rekha touched on some of those aspects of it, which is really from a server class RAS perspective. So you really need to look into that end-to-end solution to make sure that it has those RAS level capabilities that you need to deploy a solution. So a lot of focus needs to be there. The solutions are there. We just need to work together to prove those, right? But that, again, is going to lay a foundation for these composable systems as you bring them into understanding the latency bandwidth characteristics and then figure out which applications you're going to map, how are you going to use that system. Right? A pool system will just play along whatever we've identified with the expansion sort of characteristics. Right? So that's one way to look at it. Security, you can't have a solution that is at a server class without addressing security. Right? And CXL specification has addressed some of those things. As you look into what vendors are providing, they're thinking about providing the solutions. There would be certain solutions where you have an existing security solution. Can you export it to CXL attached devices and enable that? Right? So there are some plans that we'll see getting deployed that do address security, but it's really going to be important. CXL as a consortium is addressing some of the security things as we're looking forward for that. So that's going to be another important piece as we look at composable memory systems, but the foundation for that is getting laid right now. Right? And we need to just make sure as we are developing these solutions, we keep in mind what our end goal needs to be when we're thinking about composable memory systems. On the aspect of tiering, if you think about tiering, we looked at some of those use cases. We heard a lot of speakers before me talk about how they are planning to use tiering, right? Some of the things that you can see out there is, we touched briefly on TPP, right? So that's showing how you can do page promotion, demotion, right? Those kind of things. The other good, useful piece of it is, there are server-based, optimizations for how you manage tiered memory. So those you can take advantage of. Once you have a tiered memory solution, you can say, okay, I can deploy it through software, or I can make use of some of the CPU enhancements to drive this tiered memory. But once you have that solution, we really need to have that understanding of what are the knobs, how do you use it in a system, build this infrastructure so that you can work across different CPU vendors, for example. Right? So that's what we need to focus on. Another piece, I think we touched on SMDK. That's proving out to be a very useful tool if you really want to understand tiered memory and the approaches of sort of interleaving across memory. So if you are looking into saying, I want to put up a system, I want to understand the characteristics between DRAM and CXL, make use of that SMDK tool set, and you'll see some benefits in terms of characterizing the workloads. So those tools are available. You should make use of those tools as we look at that. And finally, TCO advantages, right? There are a lot of ways you can deploy a solution from a TCO perspective. The memory choices, the media choices you have, we are DDR4, DDR5, right? It's giving you the flexibility to say, you can add on in a PCIe slot, right, a memory controller. So if DDR4, DDR5 isn't for you, you're looking for more storage class memory, I think there's discussions around SSDs, CXL-based SSDs, right? So it's really opening up this for TCO advantages. There are certain things you can look at saying, can I trade off really between DDR5 and DDR4 memory as a solution? All of those things are getting enabled with what we have. Those foundations are laid. Tomorrow, even today, if you wanted to go pick up a solution and deploy it, you have all the ingredients that are getting ready in the ecosystem to enable those use cases. And finally, disaggregated memory. I don't think so we have to wait for tomorrow. There are solutions that are available that are multi-headed devices that you can pool. And making use of them and deploying certain solutions is going to allow us to understand what are all of the things that we need to focus on, right? What are the gaps? And then deploy the systems, understand from what we learn from them, feed that back, and improve the overall solution. So in conclusion, what I wanted to lay out there is, right, the foundations for what we need to build a composable memory system, you don't have to wait for CXL 2.0 or beyond, right? All of those ingredients are available today. They're coming to market, and we can take advantage of it. And as we're looking at those solutions, through the composable memory system, we can bring in some of our learnings together and then drive that, right? Just from an AMD perspective, we're starting to work on that. Ecosystem enabling will be a big part of the SDM work group or CSM work group driving that forward. Thank you.
Thanks, Mahesh and Rekha. So I'm going to cover two topics back to back. I will start off with the Intel hardware very quickly, and then actually cover the Linux implementation details. You probably might have heard about Sapphire Rapids. So the official name is actually Intel 4th generation Xeon scalable processors. As you can imagine, the Intel processors have support for PCIe Gen 5, so that is really the foundation for CXL 1.1 Type 2 memory buffer functionality. And then the host DRAM, it essentially has 8 channels of DDR5 memory, so you could essentially use a combination of near memory, which is what we call in the taxonomy, that is host DRAM, and then we have the CXL memory, which is far memory based on PCIe Gen 5. This is CXL 1.1. On top of that, there are accelerators that you can actually take advantage of. For example, we have a data streaming accelerator. It is primarily if you have paid attention to a lot of memory operations. So you have memory copy, memory move, memory set, fill operations. A lot of these operations, especially when you are actually doing the bulk movement from near memory tier to the far memory tier, you don't want to consume the precious CPU cycles. So you could potentially offload that capability through the accelerators that are available on the Sapphire Rapids platform. Data streaming accelerator is one example. We also have quick assist accelerator that can actually do the encryption and compression and decompression. So in case if you want to actually store the data, you could compress it in the far memory and then actually decompress it when you actually want to process it. So that type of flexibility does exist. Apart from that, there is an accelerator interface architecture. This is primarily meant for how do you submit a command to the accelerator? How do you actually monitor the completion of the commands? All those things are actually done through the accelerator interface architecture. So QAT as well as DSA and the other accelerators actually follow the same interface standardization. Right. So that's a combination of the DDR5 host DRAM capacity plus the CXL-based expansion capability and the accelerators as an offload is what you want to think about from a solution perspective. Data streaming accelerator, essentially, you can deploy up to 4 instances per socket. The throughput for each instance is 32 gigabytes per second each direction. So it is fairly massive from a throughput perspective that you can actually tap into. Any memory target, any memory-to-memory target is supported. So it could be the host DRAM, it could be CXL buffer, it could be non-transparent bridging based, or it could be PCIe bars. Virtually any memory target you can actually use to do the data movement part with the data streaming accelerator. From a use case perspective, the Intel processors support both combinations. So the kernel-based a way of managing the near memory and far memory, which is the top part that is supported, as well as the application-based. Mahesh talked about cache lib and cache bench. Cache lib has its own internal tiering implementation. So we could use the internal implementation as well as a way to do the offload. So the data streaming accelerator, we could use it as part of the kernel driver, or it could be used as part of the user mode application like cache lib, where you could actually offload the data transfer part between the near and far memory tiers as well. So that's kind of a quick rundown on Intel Sapphire Rapids processor and the functionality that you have. I will focus mostly on the next talk is mostly on the Linux, the readiness part. This is primarily focusing on you have a CXL memory buffer. What is the best way to consume multiple tiers of memory that is actually exposed through the operating system, and what are the constructs that are available? What things are actually currently implemented. Now, before I get into the details, the CXL buffer itself needs to be exposed as the memory, piece of memory to the operating system. Now, for that, we need to make sure that the host firmware actually recognizes the CXL device. It actually does the CXL, goes through the CXL training steps that are actually outlined in the CXL spec. And then it actually does the address decoding part so that the traffic that is actually meant for CXL media gets routed to the CXL media, not the host DRAM, and vice versa. So there is a lot of decoding programming that happens in the firmware. And then the critical part after that is really the ACPI tables. ACPI tables essentially give you a flavor of the platform, the functionality and the configuration, and which ones are memory regions, and which device is actually backing it up, host DRAM or the CXL buffers. So ACPI tables actually lay the foundation work that gets actually communicated to the operating system. The operating system can actually look at CXL. CXL memory can be configured as special purpose or conventional memory. Based on those two configurations, the behavior of the CXL memory consumption changes radically within the operating system. So if it is a special purpose memory, you essentially see the DAX device. And operating system does not do anything with it. So the intent of special purpose memory is that if you really want a fine-tuned control of the CXL memory, you can actually consume that through the DAX device, where you have to memory map it and then actually have your own custom allocator and then consume the memory. If it is a conventional memory, operating system actually manages that memory, kernel tiering will kick in, things will actually move back and forth through the kernel constructs, and everything is transparent to the application, whereas application doesn't change in that context, right? So those are the two different modes. And we have both modes that have been actually vetted out quite a bit in the working group, and we have actually tested both of them, and we should see solution recipes that actually target both of them going forward. Now, the fundamental to ACPI tables. There is one critical ACPI table called slit table in the bottom. It essentially talks about the distance between different NUMA nodes. CXL memory buffer is exposed as memory-only NUMA domain. The distances actually play a very critical role in actually making the tiering decisions. Which ones have the CPU attached? Which ones are actually farther? What is the best way to move the data is really depending on the ACPI slit table. And then when you do the NUMA control on the operating system, you can actually see the distances. And the kernel basically looks at that and builds the promotion and demotion, the sequencing from which NUMA domain to which NUMA domain it has to promote, and what is the terminal one, and all that stuff happens based on the ACPI slit table. Now, like I said in the beginning, there are two different ways of consuming. One is you could actually consume the CXL memory buffer through the operating system constructs. Everything is actually transparent to the application, so it's a virtual memory. You are actually consuming the virtual memory. When it comes to actually the placement decisions, the kernel actually does the placement. Application is not concerned about that. Of course, there are policies that you can actually use to control the placement part, and I will cover that in detail. And then the other one is really the application managed, where you have to have your own custom memory allocator, and you need to mount, memory map the CXL buffer, and then you have to do the tiering within the application implementation itself. In the Linux kernel, the memory layout is a very, very critical component. Every NUMA node has different memory zones. I won't talk about DMA capable memory zones. The big one is really the normal memory zone. That's what most of your memory actually reside under. It has different watermarks, and those watermarks actually trigger the behavior of at what point it has to start actually reclaiming the pages, and at what point it can actually do the promotion from the lower tier, and at what point you can actually start demoting the content from near memory to the far memory. So these 4 zones, watermarks actually control the behavior of when to actually do the reclamation process, when it actually does the placement, when it actually does the promotion. In the latest kernel implementation, the high watermark used to be the same watermark that was overloaded for promotion as well as the placement decisions. They introduced a new watermark called promotion so that you have enough amount of buffer. When you start reclaiming, instead of stopping at high watermark, you go all the way to the promotion watermark, and then you stop reclaiming so that you have enough buffer rather than actually doing ping-ponging behavior. Here is a quick rundown on the placement and reclamation process. So what you see is in the top, you have node 0 and let's say node n, which is CXL memory buffer as an example. When the watermark is not all the way up to low, you are essentially placing all the data in the near memory, which is node 0 memory zone. And then when it actually, in the bottom, when it actually reaches the low, that's when actually the kernel swap daemon actually kicks in, tries to reclaim all the pages, and starts moving the pages from the near memory to the far memory, right? So at that point, all the new memory allocations actually go to the far memory. In this case, it is CXL memory buffer, assuming that it is a single socket. But there are lots of permutations and combinations if it is a dual socket. Once it is done, once it reaches the high water mark, the new allocations can actually happen, on the near memory, and then the page migrations will continue to go to lower tier, and after that, the kernel swap daemon actually goes to sleep. Promotion aspect. So in the promotion, what happens is kernel task basically routinely looks at a portion of data and then marks them as soft page faults. So what happens is when the CPU tries to actually allocate access the page, it looks at the page fault, and then based on the location of the page, it may actually trigger the migration of the page closer to where your compute is. In this case, let's say if the page is actually in the CXL buffer, the page fault actually triggers the migration from CXL buffer to the near memory, which is host DRAM, before the page is accessed and executed on top. So that is the promotion aspect. Linux kernel has the NUMA memory policy. So this is there is a programmatic control. I won't go into the details. So as you can use the APIs to control the memory policies, you can essentially say, you can bind a specific piece of memory and then say this is what it's going to be and all that stuff. Or you can actually do the admin-based control through the CPU set as well as a NUMA control. And then if none of those things are actually in place, then it actually does the default policy, which is executing local to the node. The last point is I talked about the data streaming accelerator. So when you do the migrate pages, there are two different ways. One is the CPU page copy. The other one is through the DMA offload engine. Using a DMA offload engine actually frees up the CPU cycles that you can actually use it for something more impactful, compute cycles, right? So that's the Linux side of the kernel tiering, where it is today. Of course, there is a lot of work that needs to be done, but it is definitely moving in the right direction. With that, I will let Samir to talk about Windows side of the tiering and all that stuff.
Okay. As you can see, I'm not Scott Lee, so I'm representing him. We both work at Microsoft, and I'm not a software engineer, so I will try to mostly read through his slides. If you have any questions, I can take them and maybe reach out to Scott. Okay. So the message that I'm really trying to give here is Microsoft is doing a lot of work to enable this CXL memory in Windows operating system. And Reddy talked about work that is being done in Linux. Conceptually, there are a lot of similarities, but Windows is another operating system, and Microsoft is actively working on that. Essentially, right, these memory devices will have different characteristics, and they will be identified and displayed with different characteristics in the operating system. So the plan is, right, there is a general purpose memory which is there right now, and there will be a dedicated memory. And whether the dedicated memory will be exposed to customers, that is to be seen, but the work will be done. And Microsoft is actively working with most of the CXL vendors. There will be active work and making sure that all these memory modules are enabled. If you look at the general purpose memory, it's a memory pool available to all applications and managed by OS Memory Manager with paging file support. And dedicated memory is something which is not a general purpose memory, right? But it's reserved for application specific usage. Performance latency faster or slower than general purpose memory. And it can have different types of, we can have different types of dedicated memory in a system. So CXL memory can be either dedicated or general purpose, and that work will be done within the Windows enablement. So a lot of this thing is leveraging what is there in the platform firmware, where it identifies these memories and that through ACPI tables, and I think Reddy touched these topics. But the dedicated memory will be marked as a specific purpose and reserved memory to the OS. So software can have these different dedicated memory types, right? So each dedicated memory type has a unique combination of attributes, and currently the attributes are mostly latency and bandwidth, and there will be more attributes as time goes. So, and these all will be reported based on the media behind these modules. So I think this is all about the dedicated memory APIs. I'll skip this. So there are certain potential usages of these even even with the OS memory, within the OS memory manager, whether it's a faster page file, secondary store for standby pages, and secondary store for compressed memory pages. So all of that work will also be taken up at some point. And with that, I will give it to Qasim.
Hello everyone, I'm Qasim Ali from VMware. I'm a performance engineer for quite a while, more than 10 years. So I'll talk about how VMware has been working to enable software-defined memory. Microsoft and Linux have discussed some of the tiering aspects, so I'll cover how VMware is tackling transparent tiering. So at a higher level, I'm going to explain how vSphere is doing memory tiering. Conceptually, again, it's similar to what Reddy described from Intel. Let's consider that we have a host and you have two virtual machines. Let's say that you have two tiers, tier 1 being DRAM and tier 2 being a slower device. We have built a first prototype based on Intel Optane persistent memory that was available at the time. Of course, it is extendable to CXL. All it does is the Optane persistent memory also shows up as a NUMA node, and CXL also shows up as a NUMA node. We have tested some of the early CXL devices as well. So the first step we do in transparent memory tiering is we are monitoring the bandwidth of the host. So we have worked with Intel on this new technology, which is called VMWare. It stands for vSphere Memory Monitoring and Remediation. So through this VMWare work, we rely on some of the performance monitoring counters, and we monitor bandwidth of the tier, latency of the tier, and for Optane persistent memory also cache misses. So once we monitor these characteristics, as this is the vCenter product where I'm basically running a bunch of database VMs, HammerDB VMs with SQL Server, and there are a bunch of lines you can see here. You can monitor the DRAM bandwidth and also tier 2 bandwidth. In this case, it can be any device, CXL or PMEM. In this case, my device underneath is Optane. So once you monitor these bandwidth of the host, you can use this in some of the decisions. For example, the first decision you would like to do is how you can decide the tier target size. What do I mean by that is how much memory you want to allocate to a particular virtual machine based on its needs. For example, how much memory you want to allocate from a faster tier DRAM, or how much memory you want to allocate from a slower tier. And this is a function of the bandwidth of the tiers available, the number of VMs, and also the active memory. So what is active memory? I think some of the folks covered that. Gentlemen from Uber also covered it. What they have seen is the amount of memory is oversubscribed, but the actual amount of memory is not really used. So in this chart, you can see two memory counters, consumed and active. So consumed is how much memory is allocated, and active is how much of a workload, whatever is running inside the virtual machine, is being actively used, actively touched. Let's say you have a 100 gig VM, your database is, let's say, 200 gig size. And out of that 100 gig memory which you have allocated, how much is being actively used? It could very well be just 60 gigabyte, right? So you need to monitor the activeness of the workload to do this in a transparent fashion. So after you have figured out the tier target sizes, if we zoom into the VM, of course you have memory allocated to the VM. It's broken down into pages, and we want to decide where you want to put your pages. Of course, it depends on which pages are being actively accessed and which are not. So you classify them as hot pages or cold pages. Hot pages would go into your faster tier, and cold pages would go into the slower tier. And of course, the kernel would keep on doing this repeatedly after a while, just to figure out if the hot pages for some reason have become cold. So you would demote them, And then if the cold pages have become hot, you would promote them and do a bunch of mem copies. And I think some of the DSA technology I think Intel covered might be useful to bring down some of those memory copy costs. So once you have decided the page placement, in parallel we also keep on monitoring per VM level statistics, because one VM could be running database workload, one VM could be running just a batch job. So we monitor the bandwidth also through this tool, monitoring tool we have developed with Intel. We monitor the bandwidth, and you can see in this chart, I have 3 counters. One is the active memory. Previously, I showed the active memory of the whole host, which is the summation of the active memory of all the jobs running. In this case, the active memory is for each virtual machine. And then there is the DRAM read bandwidth and also the tier 2 read bandwidth. So this would go into again feedback into the system, so the system keeps on rectifying itself if it made either a suboptimal decision, and then we would keep on readjusting the tier sizes. So that's how we are sort of getting ready for the SDM ecosystem. In the previous talk, Renu touched upon some of the use cases. So I have a lot of performance results which are showing the promise of even slower tier devices. And I have seen that by adding even a slower tier device, you can increase your consolidation ratios. For example, if you have 1 terabyte DRAM, you can add 1 terabyte of more slower memory, and you can even get 2x more consolidation. If you're running 100 VMs, you can run 200 VMs. If you are interested, you can look at my VMworld talk I gave a few months ago. This is the link. If for some reason you cannot access this link, if you need to log in or whatever, I also have a video blog. I talk about some of the early performance results based on this prototype. Thank you.
Is that right? 3 minutes? 4:15. We're supposed to wrap it up by 4:15. 2 minutes. Okay, any questions? Go ahead.
Speak about CC, like confidential compute in these applications. So I know security aspects are there, ID is there, but confidential compute, like compute in memory.
Okay,
Rekha.
computational in memory and computational storage aspect, right? So
Confidential
confidential
computing, security
compute is
aspect.
also something that we are actually covering. And from the perspective of computational storage currently, smart SSDs, you can definitely come talk to the smart SSD booths, and we have speakers giving talks about smart SSD platform and how that translates to the computational memory aspect and how do we standardize. Those things are something that the computational solution workstream is going to be looking at more closely. Right, so if you're interested more in that, you should also consider joining that work group and us, right? Okay, great.
Awesome. Good question. Any other questions? All right. Thank you, everyone.